Hello, I'm Dobushovskyy, junior researcher from Carpathian branch of the Subotin Institute of Geophysics of the National Academy of Sciences of Ukraine. Today I will present joint work with my co-author and advisor, Professor Miroslav Sheremeta from Ivan Franko University of Lviv. The paper will be dedicated Banach spaces of constructed from Laplace-Stieltjes integrals. The main goal is to show that a naturally defined function space on this integral carries a complete norm. Also, Banach space, Banach structure, and to characterize what is a dual space looks like. The talk has four parts. We begin with analytic setup, what objects we and work, and which quantities control their behavior. Then we define the Banach space of Laplace-Stieltjes integrals, state and sketch the main completeness theorem, and prove the norm convergence implies uniform convergence on compact sets. In the third part, we specialize to Dirichlet series, where we obtain a stronger equivalence between the norm and uniform convergence. Firstly, we need to define what is the Laplace-Stieltjes integral. So let's by class V denote such a class of a non-negative, non-decreasing in bounded continuous and the right functions f peak on 0 plus infinity. Also consider real valued functions f small on 0 plus infinity, such that the Laplace-Stieltjes integral exists for every sigma from R and A from 0 to plus infinity. An integral denoted by formula 1 is the Laplace-Stieltjes integral. Also, two quantities play a key role in the controlling the size of E of sigma. Its mu of sigma is maximum integral maxima. It measures the total mass of the integrand, and mu of sigma is the supremum of modulo of f of x multiplied by x to e multiplied by e to power of x and sigma. It is the pointwise maximum of the integrand. Each quantity has an abscess of the convergence. Sigma mu m is and sigma mu, the critical respectively. The critical values of sigma beyond which the integral or the supremum blow up. A classical result of Miroslav Sheremeta tell us that sigma mu could be denoted by this formula. And if logarithm of f of x equals to O small of x, then this inequality holds. To describe the growth rate precisely, introduce the class omega. And a function phi belongs to omega if it is positive, unbounded on minus infinity to plus infinity, and also such that the derivative of phi is a positive continuously differentiable and increasing to plus infinity. From phi, we derive two objects. First, phi small, which will be the inverse function to phi prime, and psi of x, it will be the which is been denoted by this formula. It will be the function associated with phi big in the sense of Newton. And now we define the Banach space. Consider the reference integral j of sigma, then displayed denoted like here, represented like this, and which converges for all sigma from minus infinity to plus infinity, since if we put in the formula which was displayed above, we'll get that psi of phi of fx converges to plus infinity as x converges to plus infinity. Why also this space L as sub phi big is the class of integral which were displayed on the Formula 1, such a class of such integrals with real value f, and where f should satisfy such condition. Also, the natural norm is the supremum of modulo of f of x multiplied by exponenta of x multiplied by c of phi small of x. Addition and scalar multiplication are defined pointwise on the functions f small, making the class L as phi of f a normed linear space. The next theorem says it actually complete. So, under the standing hypothesis that phi belongs to class V, logarithm of f big of x equals to O small of x as x converges to plus infinity, then the space with such norm just defined is which is defined above, is a non-uniformly convex Banach space. Let me sketch both parts. The completeness sketch. Let's take a Cauchy sequence. I of p belongs to that class. The Cauchy sequence directly gives the pointwise convergence of f of p and f of q to some limit. One checks that f zeros satisfy the decay condition, so the limit integral e of sigma e zeros lies in that class, and the norms difference between IP and I zeros go to the zero. To prove the non-uniform convexity sketch, we exhibit a sequence of pairs in IN and Jn with unit norm whose sum has norm 2, whose difference has norm 1, bounded away from 0. So the space is not uniformly convex. The geometry is flat in some directions. This is expected for spaces of this type. Proposition 1 says that the norm convergence implies a uniform convergence on compact sets. More precisely, if E sub m belongs to goes to I in the norm, in the such norm, then I of I sub m converges uniformly to E of sigma on every compact subset. The proof is direct. Estimate. So from I minus IP minus E is under norm phi is smaller than epsilon, and we get such inequality for all x. Hence, for sigma from such from sigma to sigma 2, we'll have such inequality, such estimate. What? Let's think. What does a continuous linear functional on the class displayed above look like for this class. Proposition 2 gives us a sufficient condition. So, if lambda of big of E is displayed as such integral against the fixed function g of x with respect to f, and if the integral such integral converges and is finite, then lambda is a bounded linear functional, and it belongs to the dual space of L denoted like this. The previous one line just we just compared it by modular, and it's been represented over here. But for the discrete case, Dirichlet series, we'll see that this sufficient condition is also necessary, giving a complete characterization. So to switch from Laplace-Stieltjes integrals to Dirichlet series, we need to change in the formula of Laplace-Stieltjes integral f of x. We make a substitution by a and for x we will make a change to lambda n. Otherwise, f of x equals 0, and f of x big of x equals to n small of x, where n small of x is the counting function. And the integral becomes Dirichlet series. Well, non-Dirichlet series. So by S lambda of f, we'll denote the class of entire Dirichlet series with the real coefficients such that this condition holds. And the norm could be defined in such way. As a remark, all theorems from the integral get now specialized to this series setting. From theorem 1, we immediately get that class S lambda of phi is under norm phi. We get that it is also a non-uniformly convex Banach space. Theorem 2 is a strengthening of the proposition 1 for discrete case. Norm convergence in S lambda phi is equivalent to uniform convergence on every compact subset of R. The direction norm implies uniform is just proposition 1. For the converse, a uniform convergence on sigma 1, sigma 2 gives us such inequality. And by choosing sigma 1 in such way, it tells that the norm converges to 0. Also, theorem 3 is the main result about the dual space for the Dirichlet series. So it said that every bounded linear function lambda on such space has the form denoted like this, where d of sigma is Dirichlet series, and where g is a real sequence with such condition. Moreover, norm of the functional is denoted could be displayed in such way. So, the two-sided estimate is proved by matching upper and lower bounds. As in this slide, we'll see a sketch how the theorem 3 was proved. And as a summary, we'll have the next for item that the space denoted for Laplace-Stieltjes integrals is a non-uniformly convex Banach space when f belongs to class V and this condition holds. Also, a norm convergence in the class of these functions implies a uniform convergence of the integrals and compact sets. Also, for the Laplace series, norm convergence in such class is equivalent to uniform convergence on compact. The dual space of the Laplace series functionals is completely characterized by sequences G of n with such condition. Thanks for your attention.